3.2, we're going to deal with linear functions today. Now, guys, I'm going to ask you some quick questions here. We know what a function is, and we know how to test if a graph is part of a function. What's the test you use to determine if a graph is a function or not? Vertical line test. So if these were my graphs right here, here's quadrant 1. Here's a line. Is that a function or not? Yes, it passes vertical line test. How about this? How about this? Yeah. How about this? It's a straight line, isn't it? It's a straight line, and on here there are many points. Aren't there? There's a point here, and here, and here. If I drew a vertical line through this right here, guys, how many times would you think you did? Multiple times, wouldn't you? So can a vertical line be a function? That's my first question. The only one that's not a function up here is the one highlighted in blue. You agree? So, that being said, understand that every line or linear function that we talk about is a function under the exception of vertical lines. Anything straight up and down, not a function. Okay? Could you drive on this kind of a hill? Could you drive on this hill? Could you drive on this road? Yeah. Would you want to drive up this? Yeah. Probably not. Okay. Kind of think of it that way. Or maybe if you were skiing, I would be on this slope right here. Would any of you be on this slope right here? Okay. You understand what I'm getting at, right? Yeah. Okay. So, back in your notes here, guys, section 3.2 is titled Linear Functions. We want to know how we can determine whether a function is linear or nonlinear. Okay, I think you get the idea that linear means a line. Goals for the day. The first one is to identify linear functions using a graph, table, and an equation. We also want to look at what graphing linear functions using discrete and continuous data looks like in real life situations. And then we're going to go ahead and reverse it and write real life problems to fit some data. So, a lot going on here today, but it's pretty easy. All right, pretty easy. Let's get through this vocab here quickly. Linear equation in two variable form. All right. How about volunteer to read that first vocab term for me? Okay, an equation that can be written of the form y equals mx plus b. In fact, I think this is one of your questions today. That's going to be the solution for you. It's going to say, what's the general form of any linear function? What's general form of any linear function? Let me give you an example of what this would look like here. Let me give you an example. As an example, y equals maybe 3x plus 7. Y equals 3x plus 7. Okay? The two variables we're talking about, x and y, as they relate to inputs and outputs, like we talked about in functions last section. If you just understand this, m and b just represent some one. What's my m value here in the example I used? 3, and what's the 7? Represents which variable over here? B, doesn't it? So as long as you recognize that m and b are just some numbers, we'll talk about that down the road in terms of its technicalities, but for now, just understand that m and b are some number. Question?
Yeah, I forgot to ask about
Like a domain?
No, just
oh, independent.
Like I know when is the dependent and one
Dependent would be alone. Yep. Yep.
So in this case, y.
Y would be dependent.
So
Yep.
How come it wouldn't be x because like x depends on?
Well, basically what they're saying is this: y depends on what you do to x, and what we're doing to x is taking it times 3 and adding 7. So this depends on what you. The output here basically depends upon the input that we put in here. That makes sense? It's like saying, hey, we're going to drop a 1 into the machine. The machine's going to take that 1 times 3 and then add 7 and take out an answer for us. That's what's going on there. Okay? Yeah. Mm-hmm. Yep. Yep. Slope and intercept. Yep. You'll see that again. This section. Okay, but we're going to go a lot further in depth with that as it relates to initial values and rates of change. So, you okay with that? Good question, though. Okay. All right, so just keep in mind, m and b are just values. M and b are just values. Next one I have is a linear function. We already talked about this. It's going to be a function whose graph is a non-vertical line. So we looked at that. Nonlinear functions. graph, it's not a line. That makes sense. Solutions, basically it's an ordered pair, x and y, that make a solution true. If something is a solution, that's making the equation true, doesn't it? Okay. And a part that's probably new for you today, discrete domain, continuous domain. I want to make a sketch up here quickly. You'll want to do the same. Okay. Sometimes it's necessary to have graphs that are discrete, and sometimes it's necessary to have graphs that are continuous. And when we talk about discrete and continuous, I talk about the domain values. What values of x can I use for an input? If you can understand this part right here, discrete graphs are going to look somewhat like this. Basically going to be a scatter plot. You're going to have certain points there. Are there any lines connecting those points yet? Okay. Are there any lines connecting those points right there? So the type of graph that you have would be considered discrete. Okay? It means we're not going to count the parts in between. Now, a continuous graph would look somewhat like this. Have a start and an end, and it's completely filled in between the start and the end. All right? So if you can understand that visually, that discrete means these are a set of input values that consists of only certain numbers. When I say only certain numbers, it's like plotted points out there. However, in a continuous domain, we're talking about the points from the start and the end and all the points in between that. Right? All right, I'm going to pause this here, and we'll get to lunch. So vocab-wise, we okay on this right now? Everybody okay vocab-wise? Yes? All right, very good. Very good. All right, so let's run to page 2 here quickly and get rolling here. So linear functions is really what we're going to focus on today. Guys, example 1, determine if something's linear or nonlinear. Now, in this first graph right here, don't worry about what I have in red up here, but of the first graphs up here, one left and the one right, which one appears to be linear? Left. One on the left. You bet. The one on the left is linear. Okay? Okay, it's a straight line in blue. How about this right here on the right? Linear or nonlinear?
Nonlinear.
Nonlinear. Okay? Nonlinear. That looks like some kind of a cubic function to me. But we won't talk about that now. Sound good? All right. So if I give you graphs and say, hey, can you tell me if this is linear or nonlinear? Are you able to do that? Okay. Now, the part that's difficult might be right here. Example 2. I think this is the most difficult part of the whole lesson. I'm going to give you a shortcut to this, okay? Shortcut to this. I'll put a star by this. But instead of giving you a graph right here, I'm going to give you a table. A couple different things I can do. I can take this table and actually graph it if I wanted to. And I'll show you how we'll do that here in a second. But there's a trick to doing this right here. And I'm going to show you the trick right here. Anytime you're given a table like this right here, your job is to compare. Okay, watch what I write here. Your job is to compare change in y over, if I gotta guess what the change will be in the bottom? Change in x. Okay, it's a ratio. It's going to be something that we divide out. We're going to look at our changes in y compared to our changes in x. If the ratio after you divide turns out to be the same for each change in y over change in x, then it'll be linear. And I'll show you why here in a second. If that ratio turns out to be something different, then it's going to be nonlinear. So right here, here's what I want to do. Let me make some room here quickly. Here we go. Guys, I have a table right here. And in this table right here, we want to compare change in y and change in x. Now, guys, keep in mind that change in y over change in x, one's up top, one's in the bottom. It's kind of flip-flop the way the table would look here. Just get started right here. If I start at 9 and go up to 18, what's the change in y right there? How much do you move up from 9 to 18? 9 units. 9 units. And then how far from 2 up to 4? 2. So what I want you guys to do is take 9 divided by 2 and tell me what you get as a value. So 9 divided by 2 is 1. 4.5. All right, here's the deal. What this means is this. Got 4.5. What it means is this. For every 1 unit that I move up on the x, how much do I move up on the y? Well, that 4.5 is going to be that value, right? Check this next one here, guys. Going from 18 to, say, 27. What's your change going from 18 to 27? 9. What's your change from 4 up to 6? 2 again. My gosh, we're going to have what divided by what again? So look at that change in y over change in x. 9 over 2 again, right? Which is going to be what value? 4.5. Do they match so far? Let's look at this last change. 27 up to 36. From 27 up to 36, what's the change? 9, isn't it? What's the change in 6 to 8? What do you notice about all these ratios right here when I divide them out? They're all what? They're all equal. They're all equal, which indicates to me if something's equal like this, it's going to be linear. Now this was a coincidence because all of them turned out to be 9 over 2. You might have a table sometime that looks like this. You might have, oh, I don't know, let's go x, y like this over here on the board. Here's my table. 1, 2, 4, how about 10 and 20? What's your change of y from 2 to 4, Gabe? 2. What's your change from 1 to 2? So what's 2 divided by 1 get you? What's 2 divided by 1 get you? 2, right? Okay. Look at this next change, though. What's the change from 4 up to 20, kiddos? 16. What's your change from 2 up to 10? Isn't that 8? So in which case, now to check that ratio, I would take change in y, 16, divided by change in x of 8. What is 16 divided by 8?
2.
These match or not match? They match, don't they? So if they match like that after you divide it out, again, this example, everything was 9 over 2, so that was obvious that they matched. Over here by fraction, 2 over 1, 16 over 8, not so obvious. You have to divide them out and see what that variation constant is. In that case, it's 2. Have to be linear. Okay? Have to be linear. Now, let's check this next one right here. I'm going to change some values in this next one. Let's do this.
Change the values.
Yeah, I'm going to change these in that second table. I don't like them. They're kind of tough. We're going to jump into decimals here in a second and show you how this all ties together. Let's go with 2. Let's go maybe 3 here. Let's go 3 and maybe 6 here. And let's go 4 and maybe, oh, I don't know, 10. Okay. So let's check our change in y over change in x to determine if this is linear or not. Going from 1 up to what value here, guys? 3. So what's my change in y? Isn't it 2? What's my change in x right here? 1. What's 2 divided by 1 get me for that, guys? What's 2 divided by 1 going to get you? 2, right? All right, check my next change. 3 up to 6. What's the change here, kids? 3. What's your change from 2 up to 3 this time? Well, it's 1. Hey, this time change y over change in x. It's 3 over what value? 3 over 1 again. What do you get when you do 3 over 1, gang? 3, right? Does that match the first ratio we got out? No. When you do 3 over 1 this time, we get 3. These two meet. Are they the same, exactly the same, or are they different? They're different. That's not good. They're not equal. Okay? So is this going to be linear or nonlinear? Nonlinear. Okay, great. Nonlinear. Now, I told you guys earlier in this right here, make sure you have decimals open, right? Make sure you have decimals open. I'll give you a second to get that down here. But if you don't have your Chromebooks open to decimals, go ahead and maybe do that here quickly.
So we need to get on the Chromebooks?
Yeah, you'll want your Chromebooks, and you'll want to go to decimals.com.
Yep.
Okay. Yeah, man. I want you guys to be able to refer to that top table that we did right there. So right here, be able to refer to the XY values here and here in all these tables. And I want to show you what this looks like graphically. And I want to show you how to run this as well. All right, so in decimals, let me type this in, DE. Any of you guys having connection issues right now? Or am I the only one at this point? There we go. All right. Guys, up here, what I'd like you to do is this. Do you have a screen that looks like this right now? All right. Up here, you guys see this plus sign up there where it says add item? Go ahead and click on that. And do you guys see the option of table right here? Everybody see that option, table?
Yeah.
Okay, click that in there. Go ahead and click that. Now, guys, I just want to kind of show you this. This is pretty cool. And I think that you're going to like this for the next part that we're going to look at. But if you're not sure if a table produces a line based on looking at changing y over changing x, you can also kind of look at it graphically as well. And what I want to do is I want to input those values from that first table. So my first point, if I believe,
You believe, don't you?
was 2,9. Is that right? It was 2,9, wasn't it, right here? Okay, so let's put those in. So I'm going to go into my table here, and I'm going to punch in a 2 for x. And here for y, I'm going to punch in a 9. And then you're just going to come down here and keep clicking like that. What was after 2,9 to put in? What comes in after 2,9? 4, 3, comma what? 418. And 18. And then what was the next point? 6 and 27. And then the last point. Okay, now, here's the situation. Mine doesn't show up very well. In fact, it doesn't show up at all. You might have to zoom out a little bit. So click on your minus here.
I can't see the table that you got there.
Can you see it now?
The writing utensil thing wasn't the problem. I can't even see it from zoom in a little. I'm at the table now. Okay, now I can see it.
Let me know when you've got it, okay, John?
Okay, I think I got it.
Okay, so I'll zoom back down here. Now, guys, this is a graph that I get after I zoom out a little bit. Do those points appear to be linear or non-linear? Linear. Neat thing about this, you see this up here, this where these green dots are? If you go up there and click and hold on it like this, just hold on it, this will actually, you can pick this middle option right here, and it'll draw you a line. I kind of like to pick the third one over here. Connects the dots to dot, but does that look linear or not? Looks like a formal line. It does, doesn't it? Okay. Help me with my next ones here, guys. What were the points in the other one? I'm going to close this out and add a new table. Go to that second table and just tell me the values that we punched in. What was the first point? 1, 1. What was the second one? Was it, and then 3, 6. Was that right?
Yeah.
Okay, just looking at this right here, I'll kind of go back to the home zoom. Guys, if I connect the lines like this right here for this, I'm just zoom out one time. First of all, those look linear or not linear?
Not linear.
Okay, and if I wasn't sure, I could come into here and say, all right, well, let's just go click this option right here. Now, as my kids would say at home, Dad, that line's not straight. It looks a little bendy. Does it look like it has a few
That's what they
bends in
say,
it?
bendy.
Are there a few bends in that?
Yeah.
So is that a straight line or not? Not. A lot of information. We already knew that. Not going to be linear, right?
What number's after 4?
After 4 was a 10. Okay. So do you guys understand how to utilize this right here to be able to determine if something's linear or not? If it's a table format, whether you're looking for change in Y or change in X, or if you input data in decimals? Which one's a lot easier? It's non-linear because, as my girls would say, Dad, that's a little bendy. All right. Make sense? Okay. So guys, keeping with this theme of determining if something is linear or not, we want to go into the third example of saying, well, how do I know if a graph is linear or not? Well, we've got a pretty good tool to graph stuff, don't we? Now, I screwed up in part B. What I want you guys to do in part B is this: cross this out and write down B. This should say Y equals 5 times X. So we're just going to go back into decimals, and we're going to graph these. And we're going to say, hey, linear or nonlinear. So, right here, I think I just had a heart attack. Hunter, you scared me. That's all right. You're not the first to do that. Yeah.
The assignment didn't send through.
I haven't gotten to it yet. That's
What
why.
do we change 5x to?
Just Y equals 5x. Okay. Now I've got to figure out where my toolbar went. Home. Okay. So guys, here we go. Want to determine if the following equations that are given to you are linear or nonlinear. So here's how this first one works. Just simply going to type in Y equals 2 to the X power. So here's how you do that. Click Y equals 2. Now to get a power in here, guys, you see this A to the B button? Click the A to the B. And what am I going to throw in up for my variable? X. Whoa, there's my first graph.
It looks a little bit different, don't you?
Click on the home button down there.
How do you get the X up?
Hit the A to the B button. Hit the A to the B button there, and then put X as your exponent, because X is an exponent there, right? That makes sense? Okay. So that first one, linear or nonlinear, folks?
None.
Yeah, it's going to be nonlinear, so I'm just going to put NL right here. It means nonlinear. Okay? All right. Next one, Y equals 5 to the X. Here we go. I'm not 5 to the X, I'm sorry, 5X. So type in Y equals 5X. Green line, Y equals 5X. Linear or nonlinear? Linear, isn't it? It's a straight line here, isn't it? See the green one? So part B, what are you going to say? Linear, okay? You guys try to punch in parts C, D, and E in your decimals and tell me if stuff's linear or not linear. Okay? I'll do the same thing up here. I'm going to freeze this. La la la. La la la. How you do what?
On E, like the check marky thingy.
Square root thingy?
Yeah.
You have a square root sign down here, right by your ABC button? Sure you do. Right next to the ABC button, right to the right of ABC. See it?
I don't have A.
Right there you go. Got it now? All right, real quickly, part C, linear or nonlinear? What'd you find out?
Nonlinear.
Nonlinear. Throw my graphs up here. Unphrase it. Yeah, the 3 minus x squared, that's this purple line right here for me. So, nonlinear. Okay. How about the x minus 12 equals 12 in part D? Linear. That's this red part right down here. It's that red part right down here. And then finally, the square root of x plus 3. What'd you find out there? Nonlinear there in black, okay? That's a pretty graph, isn't it? Pretty graph. Okay. I should. Frame it and sell it. That's pure art right there. You know what would be really good? Really good, I'd say, find the area right in here, bounded by the orange, the green, and the purple one. Find that area now. Nope. It's the antiderivative of your lower limit to your upper limit of the upper function and the lower function's difference. Yeah, want to do that instead?
No.
You don't want to do calculus? Oh, come on, that's the best part. My favorite. All right. Hey, are you guys comfortable enough to use this? That's my, I guess, my main question. Are you guys comfortable enough to use this here?
Yes.
Okay. It's a great tool. It's a great tool. Take advantage of it, all right? Very good. All right. So just to clarify here, guys, you said this middle one was the second one was linear, right? Third one was nonlinear. So it alternates, right? Very good. Very good. Okay. Questions on this second page. This is pretty important, especially with the table stuff up here. You understand the tie-in from this information into decimals right there then? Okay. Well, let's take a look at the next page. As example 4, kind of a real-life example. Just want you to understand this next two examples I'm going to look at. It's going to make a comparison between discrete data and continuous data. Now, if you remember, the discrete one was like the dot graph. The continuous one was like a line graph, if you will. Okay? Example 4 says the linear function y equals 1.25x represents the cost y in dollars of x bottles of orange juice. It says each customer can buy a maximum of how much? 5. So you're in the grocery store, you're walking around, you come up to the orange juice and say, hey, we have a heck of a sale here. Limit 5 per customer. Means the most you can buy is what? 5. Well, maybe I'm a person that walks through the store and says, I don't even like orange juice. I don't even like orange juice. Do I have to buy any? No. So what are my possibilities for buying orange juice that day? Well, orange juice is good for you. I get it. Maybe I don't like it though. Maybe I'm orange juice intolerant. All right.
Carson, you don't like orange juice?
I love orange juice.
Wouldn't that be citrus intolerant?
Is it possible I could walk in there, look at the orange juice, and think, don't want any. Buy 0?
Yeah.
Can I buy 1?
Yeah. You can buy 5, you just can't buy 6.
Can I buy 2?
Yes.
I have a question. I have a question. I have a question.
Yes.
Can I buy 2.17489128544176555.4321 bottles? I couldn't, could I? It's either a whole bottle or it's not. So you're counting the number of bottles you get. So I can get 0, 1, 2, 3, 4, or what?
5.
Question becomes this. Find the domain of the function. Is the domain continuous or discrete? It's something that we don't count in the middle between 0 and 1. We don't buy half of an orange juice. Okay?
Unless someone dumps.
Unless someone dumps it. Okay?
What if it was
We'll
a
take it
half
out of context here, but this is going to be considered some kind of a graph that is what we call discrete. Basically, we're saying of whole numbers. We don't count what's in the middle. You don't count what's in the middle. You only count them by wholes, right? So 0, 1, 2, 3, 4, 5, right? So it says graph the function. Well, I'm going to make a table down here first, guys. We set our options on the number of bottles I could buy. It could be 0 up to what? This is actually going to go off here a little bit, and that's fine. That's fine. But I'm just going to label that top row up there for that table, the number of bottles that I could possibly buy in this situation. Now, up here, these are going to be considered my inputs for the following function. We're saying the cost y equals 1.25 times x right here, where x represents the number of bottles sold. So if I buy 0 bottles, what's the cost to me? $0. If I buy 1 bottle, what's the cost to me? Well, how are you going to find that? 125 times 1. Sounds like the cost of 1 bottle of orange juice that day is $1.25. How about if I have 2 bottles? What's the cost then? Which is?
$3.50.
How much? $2.50. Good. Okay, 3 times 125 would be $3.75. 4 times 150 would be, whoops, I'm getting a decimal in there, $5. And I'll just tell you 5 times 125 would be 6 1/4. Right? That'd be 6 1/4. What's that? Yeah, if it's measured in gallons, if the bottles are in gallons, that's a heck of a deal. You might just become the mascot of Florida if you drink that much. All right, so let's do this. I want to graph this and see what this looks like graphically. Now, guys, this is going to be discontinuous or discrete, if you will. Am I going to have a line here or a plot of points? Okay, let's do this. Let's label this bottom down here. Let's label this bottom down here, number of bottles that we buy. That was the X value, right? The number of bottles. And then this will be my cost over here in dollars. All right? So I'm going to label this 0, 1, 2, 0, 1, 2, 3, 4, 5, like that. And then each cost, I'll go by $1.25 because that's what each one costs. So I'm going up this way. This is 1.25. Next one will be screwed that up. 250 will be the next one. Third line will be $3.75. Fourth line will be $5. And then the last one would be 6 1/4. Maybe I should do this as well down here. All right, so quick question, gang. When I bought 0 bottles, what was the cost to us? So what's the first point I'm going to graph or plot in order to represent that cost to us? 0, 0. Okay, here it is. Right there. What's the next point you're going to plot? 1, 1.25. Next one, 2, 250. You guys see a pattern here? Okay. There's the points I've plotted right there. The points I've plotted, linear or nonlinear. Okay. Am I going to connect these points or am I going to leave them as points? Why do I want to leave them as points, Gavin, in this situation? Why not connect them? Because it's discrete, all right? It means you don't count what's in the middle. You only count by the whole number, all right? It'd be like saying we're going to count people in a room. We're gonna plot 1.35 person. 1.35 people. We're going to plot that. I don't want to see that 0.35 of a person, okay? That makes sense to everybody? All right. So leave it at is. Leave it at this. Zoom down. Okay, so this would be discrete. Now, next thing I want to look at is an example where something might be continuous. All right? How many cross-country runners in here right now? Maddie. Maddie. If I say go out and run 2 miles tonight, does that mean you go from, you just run 1 mile and then 2 miles, or do you have to run everything in between the 1 and the 2 to get to 2? So am I counting what's in between or not counting what's in between this time? I would be counting the stuff in between. This would be considered not discrete, but rather continuous. So, as an example, we have a runner whose speed is what? 5 miles per hour. He is always running 5 miles per hour. Questions here? Yeah. It says the number of miles run M is a function of the number of hours H spent running. I'm going to make a short table up here. If I spend 0 hours running, how far have I gone? 0 miles, haven't I? If I spend 1 hour running, how far have I run? 2 hours running. 3 hours running. 4 hours running. Quick question. What's 5 divided by 1? What's 10 divided by 2? 15 divided by 3. 20 divided by 4. 5. In each case, that change in y over change in x is always going to be 5, which indicates to me that this is what type of a function? Linear or nonlinear? It's linear. Okay? Would sure hope so. That's all we've been talking about. So does this situation represent a linear function? Well, you would say yes. Yes. And you would say because you run the same speed all the time. Your rate is never changing. It's always 5 miles per hour. When a rate doesn't change, that means it's going to be a steady increase or a steady decrease, depending on what type of situation you're dealing with. So, the domain of this, the number of hours is your domain. The number of hours is your domain. I'm going to ask you some questions. Your domain is going to be the number of hours. Can I run a positive number of hours? Can I run 1.3 hours? Could I run 1.26 hours? Could I run 0 hours? 0 hours just means I didn't do anything. Here's another question. Can I run negative 4.2 hours? So it looks like to me my only times that I can run are going to be from 0 and upward. Is there a limit to how long I can run? They would say infinity, but I don't know when the end of me is going to be, so. And I'm not Forrest Gump either. I would say my domain on this is the following. Number of hours, H, has to be greater than or equal to what value then? 0. You're either running 0 hours or you're running more than 0 hours. Everything at 0 or positive. So what I want to finally look at here today is what does this look like graphically? Well, we already know it's linear, right? In the discrete example up here, we didn't count the values in between because we were talking about whole values. But in this example right here, to talk about running, to go from 1 mile to 2 miles, don't I have to cover every distance in between 1 mile and 2 miles to get there from 1 to 2? Well, you do. So this would be an example of something that's continuous. So graphically, what's this look like? Well, let me clean this up here for you. Last page. Whoops. There it is. Last page here. I'll zoom up on this a bit, see what this looks like graphically. Guys, down at the bottom, we're going to say that this is the number of hours you've run on the bottom. And over here, this will be the number of miles you've run. And I'll just label these by values. 0 hours, 1 hour, 2 hours, 3 hours, 4, 5, and so on. And then I'll go ahead and list my miles. Each box I'll count as 5 miles, all right? All right, so at 5 miles per hour, guys, at 5 miles per hour, if I run 0 hours, how far have you gotten? 0 miles. So here. Next one, if you run 1 hour, how far have you gotten? 5 miles. So 1 hour, 5 miles. How about 2 hours again? Well, that'd be the 10. 3 hours would be 15. 4 would be 20. 5 would be 25. Run a couple of those. Okay. Do I want to leave this as a dot graph, or do I want to connect some stuff this time? Connected or dot, Hunter? Connected because this represents some kind of a continuous situation. Yep, it's a continuous graph. In order to get to 1 mile, you have to run through all these. You want this to go on. Listen, if I can run, if I can run till the end of time, what's that mean about my distance? It's going to keep on going. Keep on going. Okay. So that would be an example of a continuous graph. Make sure you put an arrow on the end of it, because if you don't put an arrow on the end of it, that indicates to me that line just stop. Okay? Just stop. All right. So notes-wise, guys, any questions at all? I'm going to send out that assignment here in a second, but understand the difference between continuous and discrete graphs now? All right. Hey, one thing I'm asking you to do, I don't care if it's in your Chromebook or on page 160 of your Chromebook. Whoops. Or 116 of your actual book, but take some time and look at this right here. Okay. Take some time and look at that right there, page 116 of your book. All right. There's some good examples about real life examples, very similar to what we talked about here. All right. Okay. Any questions at all? Going once.